Hello everyone. Today we are going to talk about logic circuits. So basically we people are going to start with something like we are going to discriminate how many types are there. After that we'll move forward to a few examples like adder. Adder 2 has two types, it is half adder as well as full adder. Also slowly we'll move forward to sequential circuit. These things, adder, full adder, all these things are called combinational circuit. I'll give you an explanation why they are called combinational, and all other relevant information I'll just share with you. And after that, after combinational circuits, we'll move to sequential. Sequential means it will be counter, flip-flop, a lot of things will be there. We are going to talk about slowly. Okay, so let me start with what we call as a combinational circuit. A combinational circuit is a circuit which doesn't depend on the past inputs. Like, consider this particular example. In this example we have a gate. This gate is called an AND gate. So in this gate what actually happens is that inputs are multiplied. That is, let me draw a table A, B, and let's call it an output. Output will be, in this particular thing, if the input is 0 0 0 1 1 0 1 1, then the output will be a product of A and B. That is, 0 into 0 will give you 0, 1 into 0 will give you 0, 1 into 0 again will give you 0, 1 into 1 will give you 1. So in this case this will be an AND gate. AND gate has the property of getting the inputs multiplied. So in this particular circuit you will see that there is no feedback path. If a feedback path is present, it means it obviously has to depend on the past input. But since the feedback path is absent, it only depends on the present inputs. So clearly in this type we don't have to worry about any feedback path. This has to have no feedback, right? No feedback. Okay, fine. After that we will move to sequential circuit. A sequential circuit is one which has to depend on the past input. Past input clearly means there is a feedback. Look, here we have a feedback from here. From here we are having a feedback. It is being fed back to this particular NOR gate. NOR gate also, I hope you all know the basic functionalities, the basic gates, and in case you don't, please put it in the comment section below so that I can cover that topic also. Okay, so in this particular thing we have feedback. So clearly we have to understand these few things. So this brings us to a conclusion that if the circuit has feedback, it has to be a sequential circuit, right? And if it doesn't have a feedback, it will be a combinational one. So after an understanding of how to differentiate between sequential and combinational circuit, we are going to talk explicitly about a few circuits which fall under the category sequential. Now under the category, the most important things we have is HA. It means half adder. Similarly, FA means full adder. Subtractor means a subtractor, everybody knows. So basically we are going to discuss about a 2-bit half adder or full adder or a subtractor. So let's move to half adder first. So let's talk about the half adder. Half adder means it is going to add 2 bits, bit A and bit B. These will be the inputs for the half adder. Okay, so these A and B will be inputs, and the outputs that will come out of this half adder. Half adder is basically a function. You feed one input and take one output or more than one output. Okay, so these S and C will be outputs. Now this S stands for sum and the C stands for carry. Okay, so applying the basic boolean, now 0 plus 0 will give you what? It will give you 0 and the carry will also be 0. Now 0 plus 1 will give you 1 and the carry will be 0. 1 plus 0 again will give you 1 and the carry will 0. 1 plus 1 will give you a 0 and the carry will be 1. Now a few of the students will have doubt how 1 plus 1 comes out to be 0. So for understanding, for easy understanding, I'll just tell you that binary addition is also similar to decimal, right? So in that case, 0 plus 0 in case of decimal will be 0, 0 plus 1 in case of decimal will be 1, 1 plus 0 in case of decimal will be 1 only, and 1 plus 1 in decimal will come out to be what? It will come out to be 2. 2 means if you convert 2 to binary, what will you get? If you have to convert 2 to binary, you will get 1 0. That is what I have written here. 0 means the sum bit, S, and 1 means the carry bit, right? Understood? Okay, now the main part is to implement it. So to implement, you will have to somehow derive the output to be a function of input. Okay, so clearly it is visible already that if A and B, look, A and B, if I am looking on the sum S, it is clearly visible that if we have odd numbers of 1, in here we have odd number of 1, in here we have odd number of 1, in here we have even number of 1, in here also we have an even number 0, I'll call it an even number. Okay, so in these two cases we get an output of S to be 1. It means it has to be an XOR. XOR gate is a gate which gives you output only when if you have an odd number of ones in the input. Similarly, if you now look at the carry bit, you will understand that it is only 1 only when both the inputs are 1. It means clearly it has to be an AND gate. So the implementation of half adder can easily be done by using one XOR gate and one AND gate. So to implement it here, I have taken one XOR gate. This particular gate is called XOR. This gate is called XOR, and I have taken one AND gate, and as we have derived already, S comes out to be A XOR B. A XOR B means A B bar plus A bar B. This is what XOR stands for. Okay, so A XOR B is equal to S and A into B is equal to C. I will just go into the previous slide so that you can recall it again. Look here, we have S is equal to XOR of A and B, C is equal to AND of A and B. That thing I have implemented here. A B I am taking into inputs, it will be in inputs, it will be XORed here so that we get the sum bit, and these inputs will go here as well. This is an AND gate, this will be ANDed and we'll get a carry bit. So clearly to implement a half adder we need one XOR as well as one AND gate. Now let us move forward to what? Full adder. Let's move to full adder. So in case of full adder, we are going to have three inputs basically. Three inputs means it will be A into B into C in. We are incorporating a carry input bit. That is why it is called as a full adder, because we are taking into consideration the input carry also. In half adder, the input carry is not taken into consideration. Only two input bits will be there, A and B. But here in full adder, we'll have A, B as well as C in. Now the outputs will be same, S and C out. Now again we are going to have this table. So since we have three inputs here, we'll have 2 raised to the power 3 possibilities or combinations of 0 and 1. That's equal to 8 combination. Here I have listed 8 combination, 1 2 3 4 5 6 7 8. So let us just start with it. 0 0 0 1 1 2 3 4 5 6 7. So the numbers are written from 0 to 7. Now coming to the sum with the output. Now 0 plus 0 plus 0 will be 0, and output carry will also be 0. 0 plus 0 plus 1 will be 1. So the output S will be 1 and C out will be 0. Same case here. Here 1 plus 1 plus 0 means 0 plus 1 plus 1 will come out to be 2. That means the sum will be 0 and the C out will be 1, because it has to be written like this. Now 1 0, this will be a carry out bit and this will be the sum bit. So that is why it is 0 1. Now again 1 plus 0 plus 0, it will come. This will be 1, sum will be 1, C out will be 0. same story here. This and this are the same story. Now in this case we will have 1 plus 1 plus 1 is equal to 3. 3 can be written in binary as 1 1. That is why it has been written as 1 1. This is the sum bit and this is the carry bit. 1 1 has been written here. So I hope you people have understood how the table has been formulated. This particular table has been formulated. Now based on this particular table we are going to again formulate how to implement this particular function. So again we'll have to go with the same story. Same story means I'll have to write s as a function of a, b as well as c input, and same thing I'll have to write c out also as a function of a, b and c input. Now if we take a closer look, s is 1 only when we have odd numbers of 1 in the inputs. Like here it is 1 just because we have 1 2 3 odd numbers of 1 here. Similarly here it is 1 because we have just 1 1 here, which is also an odd number. Here also we have just 1 1, that is why it is 1. Now here also, so this means it is again an XOR. It will be again an XOR. Now the implementation of carry output is a bit complicated, so to move to it we'll just take it in this way. Now C out is 1 when A is 0, B is 1 and C in is 1. So I'll just write it as A bar B into C in. A bar signifies that A is 0, B signifies that B is 1, as C in signifies that C is also 1. Similarly let's move to this one. In this case it will be, this has to be plus A B bar into C in. I hope you people are understanding. Now in this case it will be A B into C input bar, right? And in this case it will be plus A B C. If you simplify this particular expression, let me erase everything first. Now you will have to patiently simplify it. So to simplify it, I am just clubbing these two terms as well as these two terms. So this gives me C in will come out to be common and it will be A bar B plus AB bar, right? And these two terms will give me AB will come out to be common and this will be C in plus C in bar. So if I solve it further, this comes out to be C in into A XOR B. Look, it is XOR only. A bar B plus AB bar. This one is XOR. So C into bracket A XOR B plus AB. AB why? C in plus C in bar will come out to be 1 always. So we have the functions of both S and C out. So we can now move forward to implement it. Let me implement. So here is the implementation. Let me explain the implementation to you people. So we have the inputs here A, B as well as C input. Now since we have seen that S is equal to A XOR B XOR C and C out will be equal to AB plus A XOR B into C in. Okay, so this thing I am just trying to implement here. Now to XOR A and B I have used this particular gate, so the output of this gate will be A XOR B. Fine. Now I need one more XOR gate to XOR the output of this first XOR gate to the C in. So this gate has been used for this purpose. So C in comes from here, it goes here and it is XORed with A XOR B, giving us the output which is S. Understood na? This thing you understood? Let me now just clear everything and I'll explain you C out. Now let's talk about C out. In C out we actually need A into B one thing, and after that A XOR B multiplied by C in. So this A into B can be implemented by an AND gate. Here we have used an AND gate whose input is A as well as B. This is B, this is A, and the output will come out to be AB. Now this AB has to be added. Added means one OR gate will be needed. That is why here we have one OR gate. We have to OR this AB with A XOR B into C. We have A XOR B here which is to be ANDed with C. C in will be ANDed here. So we'll get an output A XOR B into C in, which has to be further XORed. This particular thing further XORed with A into B. So we get C out which is equal to AB plus A XOR B into C in. I hope you people have understood that. So for now we are just going to wind up here only, and in the next recording I'll just show you the functioning of a subtractor, as well as we are going to move forward to sequential circuits. Thanks for now. Thanks for watching. Please like and comment whatever your opinion is, and help me improve this lecture classes. Thank you. Subscribe if you like it.